Okay, so our next example deals a little bit more with some kinetic theory. We have a college student who's working on her physics homework in her dorm room. Her room contains a total of 6.0 times 10 to the 26th gas molecules. As she works, her body is converting chemical energy into thermal energy at a rate of 125 watts. If her dorm room were an isolated systems and all of this thermal energy were transferred to the air in the room, by how much would the temperature increase in 10 minutes? Now, this is ignoring furniture and everything else. So that's a entirely different situation. So in this case, what we're looking at is the rate of conversion from, we've got the energy, the thermal energy, and so that's going to be our delta U divided by time because that's power. And this is the total number of molecules. That's going to get a capital N. And this is our time. So now we need to do a little bit of work. Our N is 6.0 times 10 to the 26th molecules. And since I'm dealing in molecules, chances are I'm going to be using the K value or the KB, the Boltzmann's constant, which is 1.38 times 10 to the minus 23 joules per Kelvin. Okay. Well, we know that the power of is 125 watts, which is 125 joules per second. And we have the time is 10 minutes. Well, 10 minutes is, there's 60 seconds in a minute. That's going to be 600 seconds. So now it looks like I'm pretty good. So we can go to our equation sheet if we want. And I don't see that I have it pulled up here. But our equation sheet says that we have delta U is equal to 3/2. Ah, shoot, gosh darn it. 3/2 NK delta T. All right, this is the same thing as 3/2 little n RT, which we derived both of those equations in the lesson. In this case, I'm going to use this equation because in this equation, it deals with the total number of molecules, which is what I have. I have that many molecules, and this requires moles. I could figure out how many moles I have, but that's an extra calculation that I don't really want to do. So we're going to go with this guy. And so we're going to say delta U, which let's find delta U first. Delta U is my power times time, which is 125 joules per second times 600 seconds. And that gives me 75,000 joules. Okay. There's my delta U. Okay. N, I know. K, I know. And now I'm just looking for delta T. So now I can just plug in some numbers. So I'm going to say that 75,000 is equal to 3/2 times N, which was 6.0 times 10 to the 26th molecules, times K, which is 1.38 times 10 to the negative 23rd joules per Kelvin. And my delta T is my variable. That's what I'm actually looking for. So when I multiply, I'm going to multiply both sides by 2/3, and I'm going to get 50,000. And I'm going to multiply those two things together, and I'm going to get 80 to 80 delta T. Divide both sides by 80 to 80. And for those of you watching who are like, what the heck did she just do? I multiplied both sides by 2/3. That canceled, and I'm left with 50,000. They're not 5,000. Oops. And so you wind up with a delta T of 6 Kelvin. Don't worry, we're not worrying too much about sig figs in this course, so that's not going to be a terrible issue. Okay, I hope this helps, and how we will use kinetic theory to determine rate of energy transfer and thermal energy. In class, you'll be doing a little bit more with this, and you'll be working some problems on your own. Thank you. Have a great day, and we're all in this together.